Okay, welcome everyone to the last session of the day. So we will first listen to Manosij Dastidar, is it right? Who will tell us about asymptotics of relaxed k-ary trees.
Before I begin, I would like to apologize for not being able to be there in person. My visa was unfortunately delayed, but I want to express my sincere thanks to the organizers for still giving me the opportunity to speak today. So thank you. And because tree compression has been talked about today, that gives me a nice segue to begin my talk. Which is, well, titled as the Asymptotics of Relaxed k-ary trees. Okay, so the enumeration of directed acyclic graphs or DAGs is now an important topic in places like computer science, where you have scheduling, data processing, optimization problems, and so on in combinatorics, as well as in places like phylogenetics and theoretical physics, where they look at space-time as a causal set which can be represented using DAGs. One of these problems is the enumeration of minimal deterministic finite automata, or DFAs, with end states recognizing a finite language over a finite alphabet. Now, previously, L.V. Price, Fang, and Wallner have solved the corresponding asymptotic counting problem for a binary alphabet, and they found a very rarefied phenomenon, which is the stretched exponential. And while doing so, they structured it into, they related it to binary, compacted and relaxed binary trees. And moving forward, because they looked at the asymptotics of these things and found the stretched exponential, in this talk, I would like to extend that and ask the question of what happens in the case of the k-ary tree. So what are the asymptotics of the relaxed k-ary tree, basically? So I'll begin with talking about an ordered DAG, which is nothing but a DAG where there is a left to right ordering among the children. So what is a relaxed tree? A relaxed tree is an ordered DAG consisting of a unique source and a unique sink, such that every node except the sink has an out degree exactly k. And our main result here, as you can see, is this is the asymptotics. And as before, we see the occurrence of the stretched exponential. Okay. Let us look at some details of the relaxed k-ary tree. Like we said, it has a unique sink and a unique source. And it has, every node has an out degree of exactly k. Here is an example of a ternary tree. So you can see that everything has an out degree of 3. The, the spanning subtree created by the DFS is called the spine. The edges of the spine are called internal edges, while other edges are called external edges or pointers. All nodes except the unique sink are called internal nodes. So every internal node in the spine of a relaxed tree is associated to a k-ary tree, TU, where the nodes are traversed in post order. So if U is the leftmost leaf, we have TU equal to U. Otherwise, U has K children, U1, U2, and so on, UK. In other words, so anyway, so how do we get a compacted tree? A compacted tree is nothing but a relaxed k-ary tree, where from any arbitrary two nodes, U and V in the spine, the k-ary trees associated with them cannot be identical. In other words, common subtrees in a compacted tree are shared so that they are represented only once. These trees have been defined in the context of XML compression via tags. So let's look at them with an example. These are all the relaxed trees, relaxed and compacted binary trees of size less than equal to 3. So in this case, you notice the only one that has been cancelled out, which is a relaxed tree, but not a compacted one, because the because the subtrees are the same. Okay. So in order to count the relaxed k-ary trees, we will give a bijection to a class of paths. We do this because this makes it easier to enumerate. We define here something called a horizontally k-decorated path, which consists of an upstep 0, 1 and horizontal steps 1, 0. And it starts from 0, -1 and are given decorations. So how does it work exactly? The first step is always an up step. And if we remove it, we create a path which never crosses the diagonal y equal to x by k minus 1. Below each horizontal step, there is exactly one cross in one of the unit boxes below this horizontal step and y equal to -1. But in order to understand this better, let's look at a picture. Yes. So this is the horizontally decorated path that we're considering. It starts with an up step. And if you remove, and if you don't consider the up step, the rest is a path which never crosses the diagonal y equal to x by k minus 1. And below every horizontal step, you have a cross or a decoration. Yes. And these are the paths we need for our bijection. So this is how the theorem works. There is a bijection between horizontally k-decorated paths ending at k minus 1 n and relaxed k-ary trees of size n plus 1. So here I'm going to briefly sketch the proof without too many details of how to get this bijection. So firstly, this is an example case of a ternary tree, as you can see. We will transform this tree uniquely into a k-decorated path ending at k minus 1 n, n. We traverse the spine in post order and label it from label the nodes from 1 to 9. During our traversal, if we have every time we move up, we add a u step, an up step. And every time we cross a pointer for the first, every time we cross a pointer for the last time, we add a horizontal step. Okay, a picture would help here. And yes, so this is how we have the bijection. When we start with an up step, and then every time we cross a pointer, we put a corresponding decoration or an X according to where we have crossed it. So as you can see, we have taken this ternary tree and made it into a horizontally 3 decorated path. Yes. Okay. The consequence of this bijection is that we can now see this recurrence relation. If Rnm be the number of horizontally decorated paths ending at Nm, then this is the recursion, and the number of relaxed k-ary trees with n internal nodes is equal to Rk minus 1 n. Right. So here are the tables of values for the relaxed k-ary trees, and we can see how fast they're growing. They are also the number of unlabeled acyclic single source automata with n transient states on a k-letter input alphabet. Okay. So what would we do in the case of compacted k-ary trees? Since compacted k-ary trees are a special class of relaxed k-ary trees, we have to make the decorations slightly different, but it will be the same kind of horizontally decorated path, which we call a CK decorated path. So for every up step corresponding to an internal node, we define the tuple U1 to UK to be the labels of its children. So for consecutive HKU steps, the tuple H1, H2 up to HK consisting of the labels below the horizontal steps cannot be equal to any U1 up to UK for all preceding steps. This is again to ensure that common subtrees are shared and represented only once. So here we have the similar kind of recurrence for CK decorated paths. And we notice that the only difference, the most notable difference here is that there is an extra term here. In the relaxed setting, we did not have that. In this case, we have an extra term. And the number of compacted k-ary trees with n internal nodes is ck minus 1, n comma n. Anyway, now moving on to the asymptotics. We go back to the recursion that we discussed for the relaxed k-ary trees. And now our objective is to transform that recurrence into a new recurrence by changing the U step and extracting the super exponential and certain exponential and polynomial terms. We do this scaling, and this rescaling gives us a generalized dick-like recurrence, which you can see here with the following parameters. And so we have this, the new steps 1, 1 and 1 minus k plus 1. And we have a simple directed lattice path model with space-dependent weights. At this point, we want to look at the drift of the new model. And this drift, the drift is defined as the expected jump size when leaving ij. Therefore, at I comma j, the jump plus 1 gets this weight, and the jump minus k minus 1 gets the weight 1. So yeah. So we can see here that in the binary case where k equals 2, the first time is 0. Therefore, the drift is converging to 0 for large I. But as we can see in the general case, the drift is negative for large I. So we want to transform this, we want to get a 0 drift so that there is no systematic bias in one direction. So we effect this transformation and we get a final dick-like recurrence of this form. Right. So how do we get to the asymptotics of the relaxed k-ary trees from this point? So first, we perform a heuristic analysis of the asymptotics of Dij, and we have a good guess for and we get a good guess for the shape. Now using this shape, we will like to have explicit sequences like this that satisfies the same recursion, but with the equality signs replaced by greater than equal to and less than equal to, so that we want to sandwich it in between. We will use these explicit sequences to prove inductively later the asymptotically tight upper and lower bounds, which give us our main theorem. which is this. And just like the case of the compacted binary trees and the relaxed binary trees, we see that a stretched exponential has occurred. And here, this A1 is the largest root of the airy function, which is defined as the unique function satisfying this differential equation. I think I went too quickly, but this is what we have here. If there are any questions, I can get back to it.
Thank you very much, Manosij, for the talk. Are there questions? Can walk very slowly.
Thank you for the talk. Do you have an idea how the asymptotic behavior will change for the compacted k-ary trees? Do you have some intuition?
Yes, from what we see from here, it will look pretty much the same, but there will be some slight change in the polynomial term.
Okay, and do you have an idea if we could try to obtain some generation algorithm for relaxed k-ary tree and reject when we do not get a compacted k-ary tree in order to obtain a generator for compacted trees?
I'm sorry, I did not follow that. I can't hear you properly, sorry.
Do you have an idea to how to construct a generator for a relaxed k-ary tree? Do you have thought about this?
No, I don't understand what you're saying. I'm sorry.
Okay, no problem. Thanks.
Sorry.
More questions?
So could you explain why it was important to get a drift zero?
We want that for proper cancellations, and we do not want a systematic bias in any one direction.
We have more questions? Okay, if not, I have one. Like some terms in your asymptotics are a bit exotic compared to what we usually have. Do you know a little bit what these objects will look like and whether it is possible to get some geometric information about these relaxed KD trees?
What kind of information do you mean? I'm sorry.
What they look like. I don't know, depth, shape, whatever. Or you can just like hope to get numbers because it's just a theta and
yes, there have been like constants have been speculated, but like I don't think there is any progress in terms of the constants, what they can be in these asymptotic formulas. At least I don't know of any.
But the bijection doesn't carry any relevant information about the shape of the object? Maybe not.
Okay. Sorry, it's hard to understand. Okay.
So the bijection doesn't really carry so much information here because it's really actually a mixture of two bijections, which are not really capturing this shape, but more like capturing like the construction, which are partial DAGs on the way to getting there. But you could add some parameters. So for example, height is something one could look at basically. But and there is some guesses on what could happen. But basically what you have to do, you have to reprove always these theta results, because basically we always sandwich in between, and then you need some uniformity between these things. So in theory, it should be possible to get something on the height. And for example, in the binary key, it looks like that the height behaves like n to the 1 on 3 times. There seems to be a logarithmic term, which is quite exotic as well. So the n to the 1 on 3 could be expected, because you have to zoom into this region basically. So this is basically as well the rescaling you see, but it seems not to be the full truth. So there seems to be as well something like log n to the 2 on 3, but we don't fully understand it. And it's actually because it's not in the bijection. In order to get the height, you not only need the height, it's kind of related to the height of these paths, but also to the number of returns. And then there is a balance between these two things. And so it's a bit tricky.
Okay, thank you very much. We can applaud Manosij again.